Welcome back to the deep dive. This is where we take really dense technical stuff, break it down, and turn it into knowledge you can actually use.
Yeah, absolutely.
And today we're looking at something invisible, but honestly everywhere, distributed systems. If you're ordering food online, managing finances, even streaming this right now, you're using them.
You really are. And our source material for this deep dive is Patterns of Distributed Systems. We're starting right at the beginning, Chapter 1, The Promise and Perils of Distributed Systems.
Okay.
Our goal, our mission, if you like, is to get a solid grasp on why systems even need to be distributed in the first place.
Right.
And maybe more importantly, the immediate unavoidable problems you hit the second you try to scale beyond one machine.
That moment you scale. Okay, so that's the focus. But before we get into the nitty-gritty, the source uses this idea of patterns. Why patterns? What's the thinking there?
It's a really smart approach, actually. It helps cut through the sheer complexity. Think of patterns as standardized solutions for problems that keep popping up again and again.
Like in building architecture or
Yeah.
software design patterns.
Exactly like that, same philosophy. So instead of getting lost in, specific code implementations, we talk in terms of these bigger, reusable building blocks. It gives us a common language.
Can you give an example?
Sure. So instead of describing all the complex logic for keeping data consistent across several machines, we can just use a shorthand term, like replicated log with quorum commits.
Okay, replicated log with quorum commits. That definitely sounds like jargon we need to unpack right there. What's a quorum commit?
Right. So a quorum is basically the minimum number of members, or nodes in our case, that need to agree for a decision to count.
Like a vote needs a majority.
Precisely.
Right.
If you have, say, 5 copies, 5 replicas of some data, you might decide you only need 3 of them to confirm they've successfully written a new update before you tell the user, okay, it's saved.
So you don't have to wait for all 5. What if one is down or slow?
Exactly. That's the point. It lets the system keep working, keep committing data, even if a couple of nodes are temporarily out of action. It's this trade-off, this balance between making sure the data is consistent and keeping the system available.
Okay, that makes sense. Balancing consistency and availability.
And that core idea, how do you get agreement between machines that are far apart, especially when things are failing? That's really what this whole field and this chapter is about.
Got it. So the patterns give us this language, but let's rewind. Why do we even need multiple machines? Why deal with all this complexity? Can't we just buy one super powerful server?
Well, you can try, but the hard truth is you run into physics. Every single computer, no matter how beefy, how expensive, is fundamentally limited by its physical components.
And we're talking about those 4 core resources, right? The ones that dictate everything.
That's it. You've got the CPU, the brain, doing the calculations. You've got memory, or RAM, for fast data access.
Network card for talking to the outside world.
Yep. Network bandwidth. And finally, disks for storing data long term. These things have hard, physical ceilings. You can't just wish them faster beyond a certain point.
Okay, let's paint a picture. Imagine a server. It's handling, say, 1,000 requests every second smoothly. Then usage spikes. Suddenly, it's getting 2,000 requests per second. Does it just run 50% slower?
See, that's what you might intuitively think. But it's usually much worse than that. When you push a server past the limit of its bottleneck resource, maybe it runs out of network capacity or the disk just can't write any faster, the incoming requests don't just slow down.
They start waiting.
Exactly. They start queuing up. They have to wait in line for that maxed out resource to become free.
And that queue, that's the killer.
That's the killer. Because queuing doesn't just add a little delay. It has this cascading effect. The system's overall throughput, how many requests it can actually finish per second, plummets.
So pushing 1,500 requests at a system built for 1,000 doesn't mean it handles 1,000 kind of slowly. It means maybe it handles like 500 really, really slowly.
Pretty much. The latency, the time each request takes, just explodes because requests spend more time waiting than actually being processed. Users see timeouts, errors. The whole experience just grinds to a halt.
So the promise of distributing the system, the whole reason we accept the complexity later is just you have to. It's a mechanical necessity to get around these physical walls.
Absolutely. If you want to handle more load, more users, more data, you have to spread the work across multiple machines. It's the only way to bring more total CPU power, more memory, more network bandwidth, more disk I/O into the game.
You're fighting physics by adding more physical components,
Like I
basically.
think physics with architecture, yeah.
Yeah.
Okay, so you need to scale. The good news is you usually don't have to jump straight into some massively complex 100-node cluster. There's often an intermediate step.
Architectural separation.
Right. A very common first step is to split your system into layers, usually two main tiers.
The classic web application model, right?
Right.
Separate the logic from the data.
Exactly that. You have one part, the stateless component. This is usually your web servers, your API layer. It does the thinking, runs the business logic, but it doesn't hold on to any critical data long term.
Stateless, meaning it doesn't need to remember anything between requests.
Correct. Then you have the second part, the stateful component. This is almost always your database. It's the system of record where the actual persistent data lives.
And the immediate win here is resource isolation. Your web servers can use their own CPU and memory crunching logic.
While the database machine uses its own dedicated CPU, memory, and crucially, its own disk I/O and network bandwidth just focused on managing data, you've effectively doubled the available resources just by splitting the roles.
Makes sense.
And this two-tier setup works especially well if you can use caching effectively.
Ah, caches, the unsung heroes.
Definitely. If you can put a cache layer in between maybe storing results of common database queries or frequently accessed user profiles, then a lot of requests never even need to bother the main database.
So the web servers check the cache first. If the data's there, great, fast response. If not, then they go ask the database.
Exactly. Caches act like a shield, absorbing a large chunk of the read load, protecting that central, often more expensive stateful database server.
Okay, even with great caching, that central database server, it's still just one server, right? Eventually, it's going to hit its own physical limits. Maybe it just can't handle the sheer volume of writes, or the data set gets too big for its RAM.
That's the next wall you hit. You can buy the biggest, fastest single database server money can buy, but eventually, even that machine runs out of steam. That's the, let's call it the ultimate single server bottleneck.
So what do you do then, when even the biggest BOS isn't big enough?
That's when you have no choice left but to scale horizontally. And for the stateful layer, that means you have to start partitioning the data.
Okay, so we're not just moving the database to another machine, we're actually breaking the data itself into pieces.
Precisely. You divide your entire data set into smaller chunks, sometimes called shards, sometimes partitions. Let's say you have a huge user table. You might put users AM on server 1 and users NZ on server 2.
Or if it's e-commerce, maybe orders from January on one server, February on another.
Yeah, they're different strategies. But the core idea is splitting the data so that each chunk lives on its own independent server with its own dedicated CPU, memory, network, and disk.
And the payoff is potentially huge, right? Because now, instead of one machine handling all the queries, you might have 10 machines, each handling just 1/10 of the load.
Exactly. You're parallelizing the data access. You can handle vastly more data and a much higher rate of requests because you're throwing 10 times the hardware at the problem, but in a distributed way. Partitioning is really the key technique that allows systems to scale to, well, internet scale.
Okay, so we distributed the work for performance. That was the promise fulfilled. But
Yeah.
now we get the peril. We've gone from one machine that might fail to potentially hundreds or thousands. Doesn't that make failure much more likely?
That's the fundamental trade-off. You've hit the nail on the head. By distributing the system, you absolutely, fundamentally increase the overall probability of something failing. It's not an if anymore, it's a when and how often.
It's just statistics, isn't it?
It's pure statistics. The law of large numbers applied to hardware. The more components you have, disks, servers, network switches, power supplies, the higher the chance that at least one of them will fail at any given time. It scales up dramatically.
The book uses a really stark example with hard disks, I remember.
Yes, it's a classic illustration. Let's say you have a single hard drive. Maybe its specs suggest it fails, on average, once every 1,000 days. So the chance of it failing today is pretty small, 0.1%. You might not lose sleep over it.
Okay, low odds for one disk.
Right. But now, scale up. Build a system that uses 1,000 of these exact same disks.
Okay, 1,000 disks, each with that tiny 0.1% chance of failing today.
Suddenly, the probability of at least one of those 1,000 disks failing on any given day gets very, very close to 100%. It becomes a near certainty. You should basically expect a disk failure every single day as part of normal operations.
Wow. Just by scaling out, a rare event becomes a daily routine.
And if you have 10,000 disks or 100,000, you're dealing with a constant stream of failures. Someone, somewhere in your data center, something is always broken. It's just the baseline reality.
Okay, that leads to the obvious question then. If failure is that constant, why aren't services like Google or Netflix or major banks constantly offline? They must experience these failures daily.
They absolutely do. And that's the crucial point leading to our next section. They don't collapse because they've built sophisticated mechanisms, primarily software mechanisms, to tolerate and mask those failures. But the underlying hardware is failing constantly.
And if the failing component, like that disk, holds a piece of partitioned data,
Then that specific slice of data, maybe your user profile or a specific product's inventory, instantly becomes unavailable. Unless there's a copy somewhere else, which hints at the solution: replication.
before we get to solutions, though, the source material also highlights that it's not just about individual disks failing gracefully. It mentions Jeff Dean's famous talk about Google's data center experiences. The failures are often much bigger and weirder, right?
Oh, absolutely.
Yeah.
Jeff Dean's 2009 presentation is legendary because it gave real numbers to the chaos. We're not just talking about single components aging. We're talking about correlated failures, environmental issues, stuff you wouldn't even think about.
Like what? Give us some examples.
Well, things like PD failures. That's a power distribution unit. One of those failing can suddenly take out an entire rack or even multiple racks of servers. We're talking 500 to 1,000 machines just vanishing from the network in less than 5 minutes.
1,000 machines.
Yeah.
Gone instantly. That's terrifying.
It is. Or you get rack-level failures. Maybe a top-of-rack switch dies, or there's a localized power issue. Suddenly, 40 to 80 machines in that rack are unreachable or experiencing massive packet loss. Instant chaos, just localized.
And it's not just hardware dying, right? Network issues, too.
All the time. Things like routers needing a reload, causing brief connectivity blackouts, or even minor configuration glitches, like DNS issues that can make services seem unavailable for short bursts. It's a constant barrage of small and large, unpredictable events.
Even planned stuff causes disruption, doesn't it?
Yeah, even necessary maintenance. Things like moving racks around or upgrading network hardware. Google reported that these kinds of planned events might involve systematically taking down maybe 5% of the machines over a couple of days. So even the planned stuff contributes to the churn.
The key takeaway seems to be instability is the norm, not the exception.
That's exactly it. A large-scale system is never fully healthy. It's always operating in some state of partial failure.
Okay, let's connect this back to our architecture. We separated stateless logic from stateful data. What's the big difference in dealing with a failure in each type?
It's a night and day difference. If a stateless web server crashes, it's annoying but relatively simple. You spin up a new instance on another machine, it loads the same code, and it's ready to go. It doesn't need any history.
Okay, easy enough.
But if the server holding state fails, the one with a partition of your critical database, oh boy, that's where the real complexity bites.
Why? What makes it so much harder?
Because data has history, it has correctness requirements. You can't just start a new database server with an empty slate. It needs to recover the exact data it was responsible for up to the point of failure. And crucially, it needs to coordinate with other servers, like replicas, to figure out what the correct, most up-to-date version of that data is.
So it's about getting the state right, avoiding serving old data or worse, conflicting data.
Precisely. If you get the recovery wrong, if a newly started node thinks it has the latest data, but it's actually slightly stale, it can corrupt the entire system's view of reality. Managing that state consistency, that coordination during these constant, unpredictable failures, that's the core, the true peril of building distributed systems.
Okay, so we've established scaling is necessary, but scaling guarantees frequent, messy failures, especially with data. So if failure is baked in, how do we build systems that actually work? How do we keep the lights on?
The primary weapon against failure is replication.
Making copies.
Making copies. If you only have one copy of a piece of data on one server and that server goes down, the data's gone, unavailable until you fix that server. But if you have that same piece of data replicated, say, on 3 different servers in different racks.
Then if one server fails, the client can just talk to one of the other 2.
Exactly. The system can automatically redirect requests to a healthy replica that holds an identical copy of the data. For the user's perspective, maybe there's a slight delay during the switchover, but the service remains available. The failure is masked.
But you emphasized earlier that this isn't magic hardware failover. The software has to manage this.
100%. The hardware knows nothing beyond its local components. It's the distributed software, the control plane, that has the incredibly difficult job of 1. Detecting that a node has actually failed, which we'll see is harder than it sounds. 2. Deciding which of the remaining replicas has the most correct, up-to-date data. 3. Coordinating the switchover so clients now talk to the new master or primary replica. And 4. managing the eventual recovery or replacement of the failed node and getting it back in sync.
That sounds complicated. It's like an orchestra conductor trying to keep the music going while instruments randomly explode.
That's a pretty good analogy. The software has to maintain this illusion of a single reliable system, even though the reality underneath is constant chaos and recovery.
Okay, to build software that can handle this, you really need to understand how things fail. The source mentions it's not always just a clean crash. There are trickier failure modes.
Right. Let's break down the main types, starting with the simplest.
Okay?
Process crash. This is the easiest one. The server process just stops. It terminates cleanly or the whole OS goes down. You can usually detect this because network connections drop. Relatively straightforward to handle with replication, as we discussed.
Okay, the lights out scenario. What's next?
More complex is network delay or network partition. A message sent from server A to server B gets severely delayed or maybe lost altogether due to some intermediate network problem. Server A might wait and wait, and eventually it times out.
And the big problem here is ambiguity, right?
Exactly. From server A's perspective, did server B crash? Or is it just temporarily unreachable or incredibly slow because the network path between them is congested or broken?
Yeah.
Making the wrong call here is risky.
If you assume it crashed, you might trigger a costly failover process.
Only for server B to suddenly respond a minute later, perfectly healthy, wondering what all the fuss is about. Declaring something dead prematurely can cause more instability than the original hiccup.
Okay, that's tricky. And the third type, the source calls it the hidden killer.
Yes, the process pause. This one is really insidious. The server process itself temporarily freezes. It just stops executing instructions, but the underlying machine and OS are still running fine.
Why would a process just pause?
The most common cause, especially in languages like Java, Go, C#, is garbage collection, GC. To manage memory automatically, the language runtime occasionally needs to pause the entire application. Stop the world, pause to scan memory, figure out what's no longer needed, and free it up.
And these pauses aren't trivial.
They can be surprisingly long, especially with large memory heaps. We're talking potentially hundreds of milliseconds, sometimes seconds, or in bad cases even tens of seconds, where the application is completely frozen, unresponsive.
So from the outside, over the network, it looks exactly like a crashed server. It doesn't answer pings, doesn't respond to requests.
Precisely. Another server doing health checks might ping it, get no response, wait a bit, ping again, still nothing, and incorrectly conclude, okay, that node is dead.
And then it triggers the failover, promotes a replicate.
And then suddenly, the original node finishes its GC pause and wakes up. It thinks everything is fine. It might still think it's the primary owner of some data, but the rest of the cluster has already moved on and declared it dead.
Oh, wow. That sounds like a recipe for split brain scenarios and data corruption.
It absolutely is. Handling these temporary pauses correctly, distinguishing them from actual crashes, is one of the hardest problems in distributed systems reliability. Hence, the hidden killer label. It looks dead, but it's just sleeping, and wakes up confused.
That's a fantastic way to put it. Okay, so we have crashes, network weirdness, and these GC pauses. What other major peril do we need to worry about?
The final big one is time itself, specifically unsynchronized clocks.
Ah, right. We can't just trust the time on different servers.
You really can't. Every computer clock is based on a little quartz crystal oscillator. And these crystals aren't perfect. They drift. Temperature changes, vibrations, just manufacturing differences mean that clocks on different servers will gradually drift apart.
Even if they start perfectly synchronized.
Even then, they'll drift at different rates. Now, we use protocols like NTP Network Time Protocol to try and keep them roughly in sync. Servers periodically ask a time server, what time is it? And adjust their local clock.
But NTP runs over the network, which we already know is unreliable.
Exactly. Network delays can affect NTP accuracy. Sometimes an NTP adjustment might even cause a server's clock to jump backwards slightly, which can wreak havoc if you're trying to order events based on time.
So if server A logs an event at 10.00.01 according to its clock, and server B logs an event at 10.00.000 according to its clock, we actually have no reliable way of knowing which event happened first in the real world.
None whatsoever, just based on those timestamps. The skew, the difference between the clocks, could be milliseconds or even seconds. Relying on wall clock time for ordering across machines is fundamentally unsafe.
Even systems like Google's TrueTime, which uses atomic clocks and GPS, they still can't guarantee perfect synchronization, can they?
They get incredibly close. TrueTime is an amazing piece of engineering. But even, it can only guarantee that the clock skew between any two servers is bounded within a certain small window, maybe 7 milliseconds, for example. There's still an interval of uncertainty.
And because there's any uncertainty, you still can't use it as the sole source of truth for ordering.
Correct. That's why distributed systems often have to rely on other mechanisms to determine order, like logical clocks.
Logical clocks, how do they work in simple terms?
Instead of relying on wall clock time, you use counters or other mechanisms that track causality. The most famous is the Lamport timestamp. Basically, each process keeps a counter. When it performs an event, it increments its counter. When it sends a message, it includes its current counter value. When a process receives a message, it looks at the timestamp in the message and updates its own counter to be greater than both its current value and the received value. Then it increments its counter for the receive event itself.
Ah, so it forces the receiver's clock to jump ahead of the sender's clock at the time of sending.
Exactly. It doesn't tell you when events happened in real time, but it guarantees that if event A causally happened before event B, like A sent a message that B received, then A's logical timestamp will be less than B's. It establishes a partial order based on cause and effect, not wall clocks.
So you're tracking what happened before what, rather than the exact time. That makes sense for consistency.
It's crucial for consistency. This whole journey needing scale, hitting limits, partitioning data, facing constant failure, needing replication, dealing with ambiguity, and managing time. It all leads us to a kind of unified understanding of what a distributed system actually is.
Okay, let's try and define it then, based on everything we've discussed.
Right. So a distributed system is essentially a software architecture. It's made up of multiple independent nodes, servers, usually that are interconnected, typically by a network.
Okay, multiple nodes, connected.
They need to work together to achieve some common goal, presenting themselves to the outside world, often as a single unified service. To do this, they have to coordinate their actions. This involves communication and agreement protocols, like the quorum commits or logical clocks we mentioned.
Coordination is key.
Absolutely.
Yeah.
And because of everything we've discussed about failure being inevitable, a true distributed system must be designed for fault tolerance and resilience. It achieves this primarily through replicating data and services across multiple nodes.
So it can keep operating even when parts of it fail?
Precisely. It needs to handle node crashes, network disruptions, those tricky process pauses, and even clock skew, all while maintaining consistency and availability as best as possible. That resilience, built on replication and coordination, is really the defining characteristic. Hashtag outro.
Wow. Okay, that was a really thorough walkthrough of the foundations laid out in Chapter 1. Let's quickly recap the big takeaways for everyone listening.
Yeah, I think the key points are, first, you just can't escape the physical limits of a single server, CPU, memory, network, disk. That forces you to distribute.
Second, the main ways to scale involve architectural separation, logic versus data, and then ultimately data partitioning, spreading the data itself across many machines.
Third, and this is the big one, the moment you distribute, failure becomes statistically guaranteed. Not if, but when and how often.
And those failures aren't simple. We're talking crashes, yes, but also ambiguous network delays, those sneaky process pauses from things like garbage collection.
And the fundamental impossibility of perfectly synchronized clocks, which messes with ordering events.
Right. So the real challenge isn't just scaling up. It's building software that can reliably operate despite this constant underlying chaos.
Exactly. And that's where the rest of the source material, the book patterns of distributed systems, really comes in. The subsequent chapters dive into these specific patterns, things like write-ahead logs, different replication strategies, partitioning techniques. These are the proven solutions, the blueprints for tackling these very perils we've just outlined.
So it provides the practical toolkit for building systems that can actually withstand this reality.
Precisely. Gives you the language and the design.
Okay, fantastic. So let's leave everyone with a final thought to chew on, building on all this. It seems the fundamental question isn't if your distributed system will have a component fail or if its clocks will drift apart. Those things will happen.
They're guarantees.
The real question is your software smart enough, robust enough to handle those events in a way that convinces your users that nothing went wrong? Can it maintain that illusion of a single, perfectly reliable entity?
That's the goal. It requires replication, definitely. But that replication needs to be managed by sophisticated coordination logic software intelligence that ensures consistency. It has to prevent the user from ever seeing a state where two parts of the system disagree about the past or the present.
Keeping that promise of a unified, reliable service, despite the messy reality underneath, that's the ultimate challenge, isn't it?
That's the game.